So before we get started today, I need to make you guys aware of something. Actually, all of you are probably mostly aware of one of the things already. So this upcoming Wednesday, our next class meeting, I have a program chairs meeting that I have to attend that will conflict with this class. So I'm just going to post a video lecture from stuff that I've done previously, as opposed to physically being here on Wednesday. On Friday is our Electrical Engineering Industrial Advisory Board meeting, as well as project pitch and senior design related crap. And so all of you will be busy for that and will not be in this class. So obviously we're just not having class on Friday. So take that as a day to work on your, I was going to say work on your exam, but that's not true. You'll be busy doing other stuff for me anyway. So Wednesday and Friday of this week, Stephen will not be here and the rest of us will be doing other stuff. All right. Yeah, that's exactly what it is. All right, so today we are going to be talking about MOSFETs. All right, so as we have talked about previously, MOSFETs are formed in our CMOS process using a self-aligned gate process. So in a self-aligned gate process, we pattern our polysilicon gate, which I'm doing here in pink, and then cut out our active region like so, and we wind up irradiating this entire area that I've outlined in green for the active with ions. And just for the sake here, let's call this poly. So this length right here, from one side of the poly to the other, is what we're going to call our drawn length, L draw. And see if this is sufficiently green enough to illustrate what I'm trying to do here. Can you guys see this vertical line I'm drawing, or is it too faint? All right, so too faint. So let's try this in a different color. You know what? Let's just not do it green. Let's do it in gray. All right, so what this very small bit right here details is what's called the lateral diffusion length, or L dip, okay? So effectively, if I were to draw a transistor device over here from the top down view, this is my very thin gate oxide layer. This is the region in which I pattern my polysilicon. I will wind up having
Actually, let's put it this way. So when I do my initial implantation, I'm going to get these square-ish sidewalls here. And then when I heat this guy up, diffusion is going to expand this region slightly. And so this bit right here, as well as this bit right here, is an area in which lateral diffusion has occurred. So effectively, my source and my drain, they're interchangeable in this CMOS process, extend ever so slightly below or underneath my polysilicon gate. Okay. So what this does is it actually shortens the effective channel length of my transistor. The effective length, L, effective, is going to be my drawn length, L drawn, minus twice my diffusion length, because I'm diffusing slightly on both sides of the gate. So to minimize the effects of lateral diffusion, we can put in a lightly doped spacer implant that is deposited adjacent to the polysilicon before the heavy source and drain implants are deposited. Okay. So I'm going to draw this out really quickly here. Effectively, we would have something like this. This is our substrate. Our field oxide layer. Here is our undoped polysilicon. I'm just going to make a note of that. And then we'll have, oops, get used to using this stylus. A very lightly doped implant here. And then when we do our active layer region, it effectively lines up like so. And that light doping area, effectively because it already has some sort of dopant in there, prevents more diffusion occurring there than without it, so that we don't get a change in our channel length overall, or it's so small as to be negligible, okay? So, excuse me. So that's how we can mitigate the effects of lateral diffusion to some extent, okay? So effectively, we're trying to make sure that our source and drain implants don't undercut our gate so much that it changes the electrical characteristics of our device. We do that by putting in lightly doped implants, which means that when we do our N+ implants, in this case, if we have a P-type substrate, the diffusion doesn't extend as far as we would have without it, because there's already a concentration of dopants there. So it swells in the other directions more so than it swells right underneath the gate. All right, now we also have a thing we need to worry about called oxide encroachment, okay? So oxide encroachment is effectively going to mess with the width of our device. So if there are imperfections in the active area definition, we can have oxide encroachment where effectively, let's do this in this color. So the width of the transistor is slightly smaller than we would expect it to be. So how that happens is effectively, if you overheat this thing when you're growing the oxide back, it slightly swells over the hole and you don't get as large of a width as you want. So let's call this width W ink for oxide encroachment. This width would be W drawn. And to account for oxide encroachment, we'll have an effective width that is simply W drawn minus 2 W ink. And there's really nothing we can do to prevent this encroachment other than making the active slightly larger than it needs to be, to where when the encroachment happens, we actually wind up with the size that we want. So effectively, you just draw the active region ever so slightly larger than you want it to be, and it works out in the end if you know what the approximate encroachment length is going to be. All right. So now let's talk briefly about source, drain, depletion capacitances. The source and drain implants in a MOSFET transistor form PN junctions with the substrate or NMOS or N-well or PMOS regions, creating bottom and sidewall capacitances. So graphically, here's our P substrate. Here's our field oxide layer. Here's our N+ region that's going to form our source. N+ region that's going to form our drain. Here is our poly gate. We have a bottom plate capacitance from the bottom of our N-well, parallel with some sidewall capacitance from the three-dimensional structure of the perimeter of our N-well. We'd also obviously have one on the other side as well. Then in our we have a CMOS process inside of our N well. We have our P plus implant, another P plus implant. Here's our polygate, sidewall capacitance, or excuse me, bottom plate capacitance, and sidewall capacitances to account for there. Where the capacitance can be described as CJ SD. So this is the source drain depletion capacitance is going to be equal to C J naught B. So this is the bottom plate capacitance per unit area multiplied by the area of the source drain implant over 1 plus VSD, our source drain voltage, over our built-in voltage to the nth power, and then we'll have CJ naught sidewall times the perimeter of our sidewall over 1 plus VSD over our built-in voltage to the nth power, where CJ naught B is the zero bias bottom depletion capacitance. I'm going to put units of farads per micron squared. That is a 3, not a 2, just so that we know it's per unit area. CJ naught SW is the zero bias bottom depletion, excuse me, sidewall depletion capacitance. Having units of farads per microns. And then VSD is the potential difference between the source or drain and body of the transistor. So this VSD here, VS comma D, is not the difference between the source and the potential difference between the source and the drain. It's the source or drain with respect to the body, because that's where these capacitances are occurring. Then we have A, SD is the area of the source or drain implant. I'm going to put this in quotations, bottom plate. PSD is the perimeter. source drain implant. V naught is the built-in voltage for the source drain to body PN junction. All right. So we have some capacitance. We can also have parasitic resistance, but this is not something that you see a whole heck of a lot of unless you have effectively long runs of active region in your device. So how you might see something like this, and I honestly cannot really think of a real reason why you might do this other than trying to get creative with how you're routing signals around your chip. Would look something like this. So let's see, source, drain, parasitic resistance, okay? So let's say that you had, and again, this is going to look odd, and I'm kind of forcing oddness here just to make this, to give you an example of how this might work. So here is polysilicon thing, and then I have the metal one, and here is my contact between those two things. Then let's make this whole thing right here will be select, right? So this is effectively telling us where we are going to be irradiating N-type material. This green thing right here is going to be active. Put that somewhere I'm not going to use in a moment. And then just for the sake of argument, here's where our metal one run would go to form our source. Here's where our metal run one would go to form our drain, and then if necessary, that space between the source run of metal one and the gate run of metal one could be utilized to route signals, okay? So effectively, this dimension right here is the width of our transistor. This dimension right here is the length of our transistor. But then we also have this distance right here, which isn't really doing anything except increasing the resistance until we hit the actual metal contact. So it's that region that would introduce some sort of parasitic resistance. And it is literally just going to be the sheet resistance times however many squares we have of that thing. It is going to look like a resistance placed in series with this source of our transistor. So something like if this were drain, gate, source, and we have a parasitic resistance effectively between our, what we can call our source prime, where we would expect the source to be, and then that extra resistance over there, okay? Again, this is from the textbook. Like, I understand logistically what they mean, but I would argue that why wouldn't you move your source closer and just route your metal runs to the left? I haven't actually, in my limited experience designing what is needed for the op amps that we do in this class, ever had a reason to do anything this asinine. But just wanted to introduce it just in case.
So you're saying about routing it around something, the extra link between your source and your gate, that would be some region you might need to route something to.
Right, like we could put an extra run of metal through that region, but my argument would be, why can't we just move it to the left and make our transistor normal? And I don't have a solid answer to that question.
So instead of having your region, just like move this over here, put your routing stuff on the.
Yeah, so, I mean, in doing it this way, we run into other potential issues as well. And what I mean by that is we have metal 1, which is a conductor, over active region, which is a conductor, which means, oh no, we've also formed a parasitic capacitance we have to pay attention to as well. And I don't know that I have it on me. Let's see. Oh, it looks like I do. So what is the greater capacitance between metal 1 and N plus, or metal 1 and substrate? So metal 1 and N plus doesn't have anything listed, which means either they didn't measure it or it's too small to care about. Metal 1 and substrate is 28 attofarads per micron. So maybe that's potentially why. Maybe you actually get less capacitance if you route your metal over active than you do over substrate. I don't honestly know the answer to that question. The distances are the same. The active region is more electrically conductive. Wheels are spinning, but I'm not really coming to a conclusion in my head as to what that exactly means. But anyway, so you could accidentally introduce parasitic resistance in your transistors if you were so inclined. And I could see, I guess, potentially how this might be easy to do. So it's been a minute since we pulled out electric. So I'm going to find my mouse and just pull up electric here just for a very dumb argument. If I were electric, there we go.
Kind of reminds me of some of the problems that my group encountered when we were doing the routing for an induction circuit, because you have this huge bank of capacitors and inductors swapping charge back and forth, dumping that into the coil. And because the currents that they're running in, you had to make sure that those traces weren't too close to each other.
Oh yeah, but that's crosstalk and all that kind of stuff, which definitely is
Right, but
an
it
issue.
created routing issues with other parts.
Right.
So it was, you had to have all these parts in a certain distance from each other just for convenience. Eventually, it got to a point where we had to come up with some really weird geometries, especially since we were only doing single-sided PCBs.
And let's make it a layout. This is purely just showing you how you might accidentally do this, okay? So if I make a transistor, let's call it an NMOS transistor, I'm gonna throw it here. I'm gonna use my keyboard quickly. I'm pressing Control I to bring up the menu here to change the size, and I'm just gonna be lazy and make it a 10x2 because that's kind of the default smallest NMOS transistor I would ever make. Right now, this transistor consists of, so we have this pink bit here, which is the polysilicon. This green overlay here is the active region. Where the hole is effectively cut. And so it actually shows you how that whole area, including that run of polysilicon, is going to be doped. This bit right here, if you can kind of see this yellowish thing, I believe is defining the region of the select to show that that whole thing is going to try to be irradiated. And then this thing out here, if I'm not mistaken, is just P-well. We can figure out whether or not that's true. I'm just going to put P-well here. Yes, that's the same color. One thing that I want to point out to you guys, this was mentioned, I think briefly in class, but I don't know if I was recording it or not. And I'm asking you to do things using the wells to form resistors. If you do not click this easy to select button right here, you cannot select the well material anymore and your life will be miserable. So just as a heads up, that's where that button is located. So now I can select it or deselect it. Did I? Oh my God. Probably not. Easy to select, apply, okay. There we go, yeah, so now I can click and not click and all that kind of stuff. So anyway. So this transistor isn't capable of actually doing anything because we don't have a way to get a signal on or off, or you don't have a way to apply voltage to the source or the drain or the gate or anything like that. So to do that, I have to put an active region. I'm just going to leave that alone and then right click and boom, I have dumb parasitic resistance unless I remember to actually move that as close as possible, which I would obviously do to try to minimize the size of my drawing. That is also a dumb way you might do it. Literally just dropping stuff on there and calling it a day without trying to make things look pretty and just trying to get the functionality that you're looking for. I would encourage you not to be jackasses and do that, but that is a surefire way to introduce parasitic resistances. The way to do it properly would be to make this thing, I've had the wrong thing selected, make this thing 10 wide as well. Move it over, line it up, and then reel it in until it doesn't give you an error. No errors. Close as possible without getting errors, and then you're pretty much good to go. And you have not introduced any parasitic resistance because this is literally as close to that active region as you can be where you're making your metal contacts. So you could, if you wanted to, be dumb and lazy and introduce parasitic resistances all over the place. I would ask that you not. So that's my minor rant for that. All right, what's next on the itinerary? All right, so I'm going to talk about long length MOSFETs. We're going to have a discussion. And this discussion is purely, this is introduced in the book and I don't understand how it works. So maybe you guys can help me wrap my heads around it because it seems dumb. So layout of long length MOSFETs. How the book suggests we do this, they have two methods, one of which to me makes no sense whatsoever. And then the other of which makes more sense, but still isn't really clear of why you would want to do this. So let's start with the one that doesn't make any damn sense to me at all. Serpentine active region. So how the textbook effectively does this is they lay out a serpentine active region, as the name implies. That would look something like this. I am absolutely open to entertaining ideas here. So this is our active region. We have the metal 1 run here. And let's call this the source terminal of this device. Just for space's sake. We have a metal 1 run over here. Let's call this the drain of the device. And then a metal 1 run over here, which is going to serve as the gate of the device. Once I put some polysilicon down. And they have the polysilicon layer patterned as such. I personally cannot make hide nor hair of how this thing would ever work for a couple of different reasons. Number one, it does not obey the standard CMOS fabrication steps, inasmuch as that large polysilicon area would block anything that is designated as active as ever having a shot of being irradiated or having ions implanted. So that's problem number one that I see with this. If you guys can come up with a way this would work, I'm happy to entertain it, but at a minimum, I think you would have to alter your generic fabrication steps here. You could not use a self-aligned gate process. What's the second problem?
Your metal runs seem to be going in weird directions. You have them in parallel and then you have a perpendicular one. But
That perpendicular one is literally just because I didn't give myself enough space to make it go up or whatever, but that's not the issue here. My source and drain are the same active region. How does that give me transistor-like operation if I always have a channel? I always have a conductive path between the source and the drain. How do I turn this device off?
Are they maybe relying on parasitic resistance building up, being enough to?
So that is a distinct possibility. With that long, windy path like that, I am getting a pretty large amount of resistance between my source terminal and my drain terminal. Is that transistor-like behavior? I do not think so personally. So I honestly think this is something that the author of the textbook put in there to mess with us. I have, in my few years of teaching this class, have never yet found a student who could explain to me, and I have not figured out how to explain to a student how the hell this thing would actually yield transistor-like operation.
A, B, made, and B, why?
Yeah, like I can see how it could be made if you put your active region down and then put poly on top.
Which doesn't give you a supplementary gate process.
Right, but when your gate covers the whole thing.
See, I was wondering about that. Could it be that both the source drain parasitic resistance stuff and this design predate supplant gate processes? It's like for older technology.
Possibly. Like I could see, just since we're having a discussion here, I could see this small region actually acting like a source. And this small region actually acting like a drain if they weren't connected.
Are they actually connected in the textbook? Or is it just really hard to tell?
Maybe it's me misreading it. That's a fantastic question. I don't remember where I put the PDF copy of my textbook that I have on this computer to look at it. But this is my interpretation of their drawing, just for the sake of argument. I believe this is in chapter 5. There's always a possibility that I made a mistake when I was making these notes because I don't know for sure. Personal side story here. The first time I taught this class, my dog was very, very ill and I was having to wake up at 3:30 in the morning to give him medication. That is also when I happened to make the notes for this class. I just stayed up, made notes until 7, drove to school, taught the class. So this could be my sleep-addled mind trying to make sense of something I saw in a textbook, and I just never bothered to go back to it. But anyway, this is what our textbook suggests, or this is my interpretation through a very sleep-addled mind of what our textbook suggests as a way to lay out a long length transistor, and it does not make a lick of sense to me whatsoever. Yes.
Yeah, so it's like they actually disconnected somewhere in the middle there.
If there was a disconnection there, then yes, I could absolutely see how this could work as a transistor. If the source and the drain were not literally electrically connected together through this active region, I can understand how this would behave in a transistor-like behavior in a sense. If I have drawn it correctly and the source and the drain are literally connected together, I cannot in any way, shape, or form fathom how this behaves as an actual transistor.
Could be kind of like a variable resistor, like that enables an increase in resistance drops.
So that is a definite possibility.
Still have a transistor.
Right. So as you applied a different voltage at the gate, what would that do? That would, let's see, so it's positive voltage, so that would attract electrons towards the topmost surface. Because that area becomes more conductive, then yes, I can see a very odd potentiometer / rheostat-like behavior out of, I guess it would have to be a potentiometer because it's 3 terminals. No, it would be a voltage controlled rheostat because it's the resistance is only between the S and D terminal. Anyway, that's nitpicky. It sure as hell ain't a transistor. Were you able to find the, no, okay. All right.
Outlook has changed, kind of like index stuff, and like search doesn't work anymore. It's trash.
Okay. All right, so now the way that makes sense, but is arguably dumb. At least this way makes sense. Series transistors. So in this particular configuration, let's say that we have a section of polysilicon that looks something like this. We have these fingers. Let's close that off there for just the sake of argument. I'm going to put a run of metal 1 here. And then I have my contact for my gate. And I have this active thing here. Let's just call it N-active for the sake of argument. I could throw metal 1 here. Metal 1 here. Contact, 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 contact. So let's just say, for the sake of argument, that this is the drain and this is the source. So why this makes sense to me is effectively we have just connected 3 resistors, or excuse me, 3 transistors in series. And so what I mean by that is on the left-hand side, we have our drain. And I'm going to call this G1. And this is S1 and the drain of 2. So this is what this looks like effectively to me. All of these gates are tied together to make our gate terminal. This is the source of 2, which is also the drain of 3, like so. So effectively, this region in between here is the source of 1, drain of 2. This region is the source of 2, drain of 3. This region is the source of 3. This region is the drain of 1. So if each of these had different lengths, call that length L1, L2, and L3, and all of them have the same widths. So this one would have an aspect ratio of W over L1. This one would have an aspect ratio of W over L2. This one would have an aspect ratio of W over L3. In all, this would look like W over L1 plus L2 plus L3, which does, to me, make transistor-like sense. My question, and another thing I have not actually been able to figure out yet, why you wouldn't just make the polysilicon longer. Like why you wouldn't just do something like this. Where this length right here is L1 plus L2 plus L3. Here's our drain. Here's our source, and then up here, we would attach our gate. So I understand fundamentally how that behaves as if it were a long length transistor. What my problem with this is that by interdigitating the gates like that, it actually takes up more physical space than if you just made a large gate. So I fundamentally do not understand what the benefit of this is either. So, yep, I don't know what else to say. Like,
For me, it just keeps coming back to this idea that maybe it's limitations of whatever process they're using.
possibly, and that could be very, very true. The material that this came out of could have been from the first or second edition of the textbook before the self-aligned gate process became so prevalent. That is a definite possibility. I honestly need to look through some of the other textbooks that I have on the matter to see if it's mentioned. I may, as I restructure this class, just drop this bit entirely because it fundamentally does not make sense with my understanding of these processes. But my understanding of these processes begins circa 2008, which is 20 years after the self-aligned gate process came to be a thing.
What's going on with this?
All right,
They just, yeah, the textbook just says, oh, this is how you do it. It doesn't
no explanation whatsoever.
why you would want to.
Yep.
It does say it minimizes area by sharing drain and source connections between MOSFETs.
But how does it
Right.
use less area? Like, I understand.
Showing you what this says.
Yeah, no.
And you're just showing us what it is.
Like I read that myself, and that was probably where the beginning of my incredulity, or whatever the right word is there, came from. Because in making a beta multiplier device, it requires a transistor with a very odd aspect ratio. And so I decided to make it a long length transistor, and I made it in two different ways. One of ways was using an interdigitated scheme like this. And then the other way was just making it with a really, really long run of polysilicon. And there were no difference in the electrical performance whatsoever, but the one with the really long run of polysilicon was physically smaller. And where in designs where space is at a premium, physically smaller wins, right? That's something that we haven't talked about too much in this class at all, and that is why we are paying attention to the analog integrated circuit behavior. Anybody have any thoughts on that? So the reason why we are learning about techniques for designing and laying out analog integrated circuits is because for a digital integrated circuit, it largely scales pretty easily. So as your technology nodes get smaller and smaller, the circuits get smaller and smaller. You do have to pay attention to things like heating effects and all of that kind of good stuff. That's where your maximum limitations are going to be. But on a mixed integrated circuit where some portion is laid out for digital and some other portion is laid out for analog, the digital portion keeps getting smaller and smaller, but the analog portion is roughly staying the same size even 20 plus years later, right? So figuring out how to make it as small as possible is generally accepted as better because we get smaller and smaller chips. It is the bottleneck for reduction in a mixed signal IC like most modern electronics use.
You can shrink it down, more chips per wafer.
Exactly right. So effectively on a modern integrated circuit, you have some area allocated for digital integrated circuits, you have some area allocated for analog integrated circuits, and you have some area set aside for MEMS. The size of the digital integrated circuits and the size of the MEMS consistently gets smaller over time. The size of the analog portion has not. So just figuring out effectively small things to make things as small as they can, small changes to make things as small as they could possibly be can actually save a lot of space because you're talking about the biggest part of your IC.
I guess that's why analog devices just cost more.
Yeah, they have to be physically larger, yeah. So anyway, all right, so the last thing that we're going to talk about today is the layout of long width MOSFETs. And guess what? This actually makes sense. It's a wonderful thing. This is something that we will actually use very regularly. So if we run transistors in series to get long length, if we run them in parallel, we get long width, okay? So we're going to do effectively the same thing that we just did. We are going to have a series of interdigitated fingers. Let me give myself a little bit more space than this. Because we're not just going to have blank regions in between here. So this is hopefully fairly obviously going to be our gate. Here is our large active region. Effectively, it looks exactly the same as our last thing. This dimension gives us our width. Now what we are going to do is we are going to tie together every other region of silicon. Or implant, I guess would be a better way to put it. Like so. I'm just going to draw dots for the contacts because I'm tired of drawing shitty squares. So this region up here is our drain. This region down here is our source. And so effectively what we have, all our gates are electrically connected. So let's look at things here. So this is a source for transistor 1. This is a drain for 1. This is our source for 2. This is our drain for 2. This can be our drain for 2 as well. So effectively we're sharing drains. This could be our drain for 3. This is our source for 3. And then this might be our source for 3 and 4. So that effectively what we have here something like this. Here's our gate. So all of our gates are tied together, all of our drains are tied together, all of our sources are tied together. This looks like a single transistor that has an aspect ratio of 4 times the normal length divided by the length. So this actually saves space and it's actually used quite a lot, okay? So as it happens to work out in a lot of process technology nodes, the mobility of electrons is usually, well, it's pretty much always larger than the mobility of holes, but so in a lot of standard processes, it's usually a simple ratio between the two. So for example, if you want to get the same electrical performance out of a NMOS transistor as you do a PMOS transistor for a C5 process, PMOS transistor needs to be about 3 times as large. So instead of making one that's physically huge, you just put 3 10x2s in parallel, and it's the exact same thing. So it makes for very easy and repeatable design. All your transistors effectively start out the same size, and then when you need a larger one, you just wire a couple of them in parallel and call it a day. So this is actually something that gets used quite a lot, and it's extraordinarily useful that we can split them up like this and make it behave in this particular way once we do figure out how to do matching between transistors, because this is how we can subdivide a single transistor into however many smaller transistor parts we need to make up a whole for our matching schemes. It's just by wiring them up in parallel. So this bit actually has use. Hooray. All right. So it's 1:45, so that means we're done and senior design starts in 15 minutes. So I guess I have to go wolf down the rest of my lunch.